As I said earlier, they're just delighted to see you all coming this afternoon to join us for this seminar to look at atmospheric nitrogen impacts on Northern Ireland's semi-natural ecosystems on this notable day, which is the Clean Air Day. Clean air and the need for it is a priority issue and objective for the department, given the risk and threat that it poses, poor air quality poses for human health and the natural environment. I'm joined this afternoon by my colleague Anya O'Reilly from NIA Natural Environment Division from the Air Quality and Biodiversity Unit, and by our close colleagues in UKCH, Uli Dragstedt and Nettie Van Dyke, who we have had the pleasure of working together over many years, trying to get to the bottom of the nitrogen and ammonia issue and understanding what impact it's having in the natural environment. This afternoon session, we plan to go through a series of slides just to kind of give you an update and a selection of results from our ongoing evidence programme, which has been designed to understand, address, I suppose, understand and monitor and address the atmospheric nitrogen impacts on our ecosystems, and to see how we can best use that evidence to inform policy going forward. So there'll be an intro from myself and Anya, and then Uli and Nettie will take us through more of the results around the monitoring on sites and the impacts in terms of the biodiversity indicators, I suppose. And then that also allows us then to have a bit of a wrap up time and try and leave about 10 or 15 minutes for questions. Again, the nature of these presentations are pretty technical. We will try and make sure that they're as understandable as possible. But again, please use the Q&A function to insert any questions throughout, and we will be picking them up at the end. Also just pointing out that this seminar will be recorded, and then that we will be able to share it afterwards with others who haven't been able to attend. So without further ado, if we move on to the next slide there, Claire. Back up. Okay, really just I'm just going to have a few slides here just to set all of this in context. Why does ammonia and pollution and getting it under control important? And you'll see here that it does play into and play a large role in how we address today's three big challenges, which is climate change, which we're all very, very concerned and aware of, the very close link to biodiversity, and closing that loop is how we handle and address pollution. We need to address all three together and make sure that we are developing coherent policies and programs and plans to address all three, because having attended both climate change and biodiversity COPs, COP 26 and 27 and also COP 15 are almost one and the same, given that the inextricable links between nature recovery and climate action and climate change, and also how we address that third big issue, which is pollution, which is on the increase, but is massively interfering with our natural environment's ability to cope with and adapt to climate change, and also to make sure that we can have it resilient enough to store and sequester carbon for us. So just kind of keeping that in context, that we need to be addressing all three as part of a nexus approach. Next slide, Claire. Central to this, and that what has been discussed at all of those COPs that I referred to, it is the need for us to halt and reverse biodiversity loss. For us to be able to have, as CCC are asking us to have, a well-adjusted climate resilient landscape. So this will require us to have halted and reversed biodiversity loss, and make sure that our ecosystems are all fully functioning and able to help us with adaptation and mitigation. There were very clear targets set out and agreed in December in Montreal. So the UK and another 192 countries signed up to the Kunming-Montreal Global Biodiversity Framework, and that will form the basis of our environment strategies and nature recovery strategies going forward, and ultimately underpin all of our climate action and green growth activity. Next slide. Next slide, Claire, sorry. Yes. So to be able to deliver that and achieve that goal of being nature positive by 2030, these are the 23 targets that have been set out in the Kunming Montreal Biodiversity Framework, because all of these components need to be in place for us to be able to reverse the biodiversity loss, restore our ecosystems, recover nature, and therefore be able to cope with climate change. As you will see, if you just click the wee next button there, central to this is ensuring that we're addressing the drivers of biodiversity loss and that we're tackling any of those issues that reduce and negatively impact on biodiversity. So there is target 7, as we refer to it as, is much longer in words as everything in those agreements are, but ultimately the goal is to reduce pollution to levels that no longer harm biodiversity, and in the first instance by 2030 to have reduced by half those losses to the environment, including things like pesticides, but more notably and relevant for today's discussions is nutrients. Nutrients, nitrogen, phosphorus, all of those things are having an impact. So we need to be able to address losses to air, water and land. So as you can see, there's a lot to do, but there is that need for that better understanding of how all of these things interact so that we can make sure that any of our activities and policies and programs going forward target as many of these issues as possible in order to achieve the success we need. So without further ado, I will hand over to Anya to set more of the context for ammonia in Northern Ireland.
Thanks, Sarah. Just checking everyone can hear me okay. Is that
yes,
fine?
All good, yes.
All good, okay. Thanks for that, Sarah, and outlining, I suppose, our biodiversity obligations and why all of this is so important. I'm just going to quickly give an overview of the key sources of atmospheric nitrogen. So the main one, obviously, we're going to discuss today is ammonia, and it's mainly derived from agricultural practices, primarily through manure and fertilizer management. You can also see there's, also some other images there which outline other sources. Some point sources include large international seabird colonies and seal colonies, but in terms of an NI perspective, it's agricultural practices that we're talking about here. Next slide, please, Claire. We also have oxides of nitrogen that are emitted to the atmosphere, mainly from combustion of fossil fuels, from industry, from domestic housing, and from transport. Next slide, please, Claire. Okay, so this slide just briefly shows the UK emission trends and the fact that there's been policy success for sulfur dioxide and oxides of nitrogen. So as you can see there, if you look at the SO2 graph, there's a 95% reduction in SO2 from the peak in the 1970s. And if we look at the NOx graph, there's also been a 75% reduction in NO2 from the peak in the 1990s. If you draw your eyes down to the lower graph, which shows ammonia, the emissions there are, there's very small reductions occurring or they're remaining stable. So it's much more stubborn. There's been less, I suppose, policy implementation there to try to drive those emissions down. Next slide, please, Claire. So in terms of an NI perspective on atmospheric ammonia trends, the agricultural sector accounts for the majority of ammonia emissions in NI, as I've currently said. And we do also have other small sources, which include transport and waste processing, domestic combustion, internal industrial processes, but the majority is dominated by agricultural practices. And the 2023 statistics report has shown that emissions from agriculture have increased 9.1% from 2001 to 2021, and this this is quite different in terms of what you see in England and other places, in that they've seen a 14.8% decrease across the same time period. Next slide, please, Claire. So now we've gone over, I suppose, where atmospheric nitrogen comes from. I'll give a quick summary of what happens once it's emitted as ammonia or nitrogen dioxides. So as you'll see, just as you follow the arrows, a proportion of the atmospheric ammonia will drop out as dry deposition close to a source such as a farm, a road, industry. There will also be reactions in the atmosphere with gases, particles, and water. And the atmospheric nitrogen will disperse and travel longer distances in the atmosphere before being washed out in the rain as wet deposition. There's also nitrate leaching as well, but we'll not focus on that today. That's just a very quick overview of the nitrogen cycle. Next slide, please, Claire. This is where I hand over to UKCEH to give an overview, I suppose, of all of the work that we've been working on over the past series of years. So handing it over to Nettie here.
Yeah, we have now seen that where the nutrients are coming from and where they are going to. But of course, it's also really important to know what the effects are. Why are we so busy with all these kind of things? We have first the ecosystem effects, and that means especially the ammonia and the NOxes have really an effect on the plant species and the plant community changes. And indirect about that, when species are disappearing, it means that insects and, for example, butterflies also disappear. So it's a whole kind of a chain that follows up on the disappearing of species. It's not only that they're disappearing, they have also an increased sensitivity to droughts, frost, pests, pathogens, and all that kind of things. And last but not least, with disappearing, especially the peat moss community, if the plants are dying and we lose the active peatlands, which are an enormous storage which have an enormous storage available of CO2, we lose that kind of CO2 storage capacity. Not only are there effects on ecosystems, but also on human health. There are measurements done that people have more problems with asthma, and also there are other major health issues like diabetes, low birth weight, and dementia. In this talk, we are not talking about the human health because we, in our research, know not so much about it, and we know far more about the ecosystems. Next slide, please. Here is a big example, or a very clear example from, on the left-hand side, a healthy community of bog moss, the sphagnum mosses, and on the right-hand side, the damaged sample. It's a really used difference between that. And as you can imagine, the damaged species of sphagnum don't keep a live peatland intact and they disappear. Next slide, please. It's very difficult to tease apart the results from the dry deposition and the wet deposition. Here is an example from an experiment in the south of Scotland called WIMBOG, where we have an experiment with the dry deposition. On the left-hand picture, where you see the white pipeline, ammonia is fumigated over the bog. It was really a healthy bog, and in the distance, in the back, you can still see that it is healthy and heather is growing as sphagnum. Close near the pipe, a lot of the sphagnum and other sensitive plants have disappeared, and the cotton grass is coming back. On the right-hand side, you see a picture from above where you can really see that the damaged area is increasing. It is increasing over years because this experiment is now running for 20 years. What we also have seen in this experiment is that the dry deposition, so the ammonia gas, has a much bigger effect on the degradation of species and also really faster than the wet deposition. Next slide, please. Here again, an example from the damage that the ammonia can do on Cladonia, reindeer moss. This is again a result from the Wim Bok experiment. Shortly after the experiment started, within 3 months, we could already see damage done to the Cladonia. It was turning pink and bleaching. And further away, within 3 years, a lot of the Cladonia had just completely disappeared. We have, as a result, it was going further and further. We have photographic evidence, as you can see here, to underpin this kind of thing. Next slide, please. It's not only that there is a lot of damage to certain species, there are also species that just love the more availability of nitrogen. But that also includes then that the vegetation type, the habitat type is changing. Here on the top of the slide, that are the vegetation species that are disappearing, and on the bottom, the ones that are appearing. It's not that they are bad or something like that, but it's just the type of vegetation is disappearing. And as we are especially speaking about bogs this time, if the bog vegetation is disappearing, the living peat community is disappearing, and the CO2 storage capacity is disappearing. We really need to take that into account. I hand now over to my colleague Uli. Next slide, please.
Hello, I hope you can hear me too. Yes, great. So how do we measure and how do we decide whether there is a vegetation effect apart from just looking at the plants? There are what's called critical levels and critical loads thresholds, which are depending on the sensitivity of different plant species or species groups or habitats. So the critical levels just refer to ammonia and their annual average concentrations in the air in micrograms per cubic meter. And there are 2 critical levels. One is at 1 microgram, which is for all lichens and mosses, and the other one at 3 microgram with an uncertainty range of 2 to 4 for all the other higher plants. The critical loads are for nutrient nitrogen deposition. So this is the dry and the wet deposition that Anja has mentioned. And this is not just from ammonia sources, but also from the NOx sources. So it's all the atmospheric nitrogen deposition. And the sensitivity of habitats and plant communities is quite different. So we have different critical loads, and they're expressed in terms of kilograms of nitrogen per hectare, a bit like a reverse fertilizer application rate. And with these critical loads and levels, you then have excess nitrogen, so above the critical load or the critical level. So it's not just whether something is exceeded or not, but it's by how much is it exceeded. And the aim is with mitigation to bring it down and ideally bring it below those thresholds. Next slide, please. So remember, we've talked about critical levels of 1 and 3 micrograms. This map shows the most recent ammonia concentration maps modeled for the UK and Northern Ireland in a zoom in. And you can see that below the 1 microgram, which is the healthy threshold for lichens and mosses, that's the blue color, there's very little in Northern Ireland that is considered safe. And if you think about the 3 microgram threshold, that's the darker orange. That's where the threshold is for the higher plants. So there's quite a chunk of Northern Ireland that's above the 3 micrograms as well, but it's the 1 microgram that's exceeded almost everywhere. And if you look at the little map in the corner for the UK, you can see that Northern Ireland as a whole is quite severely, has got quite severely high concentrations compared with most of the rest of the UK. Next slide, please. So if we think about nitrogen deposition, which is then linked to the critical loads from all nitrogen, not just ammonia, there are different ways of calculating this for the different habitats. So, for example, the low-growing semi-natural habitats, such as the bogs and the heathlands, they have a lower deposition rate than, for example, woodlands, because there is more leaf area in the woodlands, so they can filter out and get more of the dry deposition. The wet deposition just comes down with the rain on everything in the same way. So what we're showing you here is the nitrogen deposition calculations that are applicable to bogs and heathlands and other low-growing species. So again, you can see, if you remember where the concentrations were high, you also get the high deposition. And again, in the context of the UK, Northern Ireland has got quite high nitrogen deposition. Next slide, please. So there are annual reports carried out for the UK and its constituent countries, which are referred to as the trends reports. This is from the latest report published last year. The new one should be out in the next month or two. And it shows that elevated ammonia concentrations and N deposition are a substantial threat in Northern Ireland, with very large areas of the country having annual mean concentrations above the critical levels. So these data are for the previous year, whereas the maps I've shown you are kind of a preview of the new report that's not quite out yet. But you can see that the huge percentage of Northern Ireland's nitrogen sensitive habitats that's exceeding the 1 microgram critical level. Not quite so much exceeds the 3 micrograms, which is something. And in terms of the designated sites, again, large parts of the Northern Ireland sites exceed both the critical levels and the critical loads. And you can see the numbers there for yourself, with the vast majority exceeding both types of thresholds. Next slide, please. So what are we doing about it? How do we quantify with measurements as well as with modeling? So we do lots of ammonia monitoring, which is really important for verifying these national modeled estimates and the maps that I've just showed you, and to quantify the level of the threat to the designated sites at a different spatial resolution from the national modeling. And that also brings us to the local sources, because on the ground we can look at local sources much more easily than in the modeling, which relies on data availability and is more generic than we can do when we really zoom in somewhere closely. And we can also understand the spatial and the temporal patterns better with local quantifications. And it's important not to just look at the ammonia concentration, but also to combine it with the vegetation assessment, and nitrogen content of plants and lichens and mosses is a very good way of seeing how much are they actually taking up. So we've established monitoring networks for several designated sites in Northern Ireland. Next slide, please. And at this point, I hand you back to Nettie.
Yes, as Uli already said, it's really important not only to look at the air concentrations, but also what it's doing on the vegetation side, because that's where the damage is done. And again, we can look at the damage what is visible, and that's clear, but we also want to do something to see before we really see the visible damage, and if we can have more something that is easier to measure. And a standard method for that is the nitrogen content in the vegetation, the percentage N. This works especially good if you have, say, a source of the ammonia. That can be a farm or whatever. And then nothing else in the area. Then it has a really, really good relationship with the ammonia concentrations that is lowering down from the source away. In previous work, we had looked at quite a few biomonitoring methods because we wanted to see if there was more than the percentage N that we can use. Another method, again a chemical method, showed that showed more sensitive is the ammonium content of the vegetation. That's why we are using these two methods in Northern Ireland. On the pictures you can see that there is quite a bit involved in this kind of sampling and measurements. First you have to collect all the samples in the field, and then you have to sort and clean all the vegetation samples and to extract the volume from the vegetation samples, which you can see in the right bottom picture. The different vegetations show different colors, which is quite colorful to see. But it's also really important to have different species analyzed for it because every species react in a different way. Next slide, please. Here is an example from the foliar ammonium for a few sites in Northern Ireland. On the really left-hand side, the green squares, there are the results from Loch Navar, which is a really clean site in the west of Northern Ireland. So on the x-axis, the ammonia concentrations goes from really low and clean to high on the right-hand side. On the other axis, the y-axis, is the foliar ammonium content, and that goes from really low at the bottom to high at the top. You see here different sites. The red and blue round circles are from Moninea. That is a site where that was really damaged, had damaged vegetation, mainly because there was a poultry farm really clear by. That poultry farm got closed, and a few years after the closure, we were able to go back there to do some more measurements. To compare this site with the Ballynahoe site, which are the purple triangles as a kind of a cloud in the middle. So that means the ammonia concentration there is relatively high, at least at some of the sites, because as Uli and Anja already have said, we have measurements at more points on that site. It's not only from one point, but we have 9 points there where we sample the air ammonia concentration, and that are also the same sites where the vegetation samples have been taken. To compare that with another site with relatively low concentration, Gulga, which is a quite high altitude site. And we see here a bit of a higher foliar ammonium concentration than you expect on the basis of only the air concentrations. So we are thinking what is going on there. We are thinking that there might be, because it's a high site with high precipitation, that they have more impact from the wet deposition, and that's why there is also be started with a wet deposition collection. In fact, it's a bottle to collect the rain. Next slide, please. Here in the graph, you can see roughly the concentrations from the air pollution, the air ammonia measurements. We started with 5 sites and they have a similar pattern. The first 4 months were a little bit difficult because we set the site up just before the COVID period started. So the people were not able to change the samples for a long period. But once they were changed, after that they were changed every month. And you can also see that there is a seasonal effect with a little peak in August, and it's going up again in March. This is only from a 14-month period, but it's well below the critical level for the lichens. But we did see at some points more damage on the vegetations than we expected. Again, the question is why? What I already said, other forms of wet nitrogen were going there, the wet deposition. That's why we started the wet deposition. But we also have to take into account that there might be other factors that do damage to the vegetations, like there might be still an effect of historic overgrazing. We don't know, but we are continuing to measure there. Next slide, please. Yes, this year we had in spring we spent more than a week in Northern Ireland to collect about 170 samples together with people from Ulster Wildlife, National Trust, DERA, and we collected samples from several bogs in Northern Ireland. So the analysis is in process at the moment, so we are really looking forward to see the results from this and see how they compare with our existing results. Next slide, please. After, of course, we want to know what happens if the concentrations are going down. Is there some recovery? We have an example at Monineer Bog where, as mentioned before, we were able to go back after the closure of the poultry farm. And we did measure the air concentration, and we did see that the air concentrations had come down a really lot. It was still a bit high because of nearby sources, but the really high concentrations were going really down. So that's a good sign and a must for recovery, but there are other factors. For example, the nitrogen can be still in the system and going around as a cycle, and it takes years before the vegetation can show signs of recovery. Another factor is, especially for the peatlands, that the water table must be high enough to have a healthy peatland. And also overgrazing, trampling of animals can do quite damage. But we have to be sure for a good recovery, all these factors need to be in a good position. Next slide, please. Here there are a few pictures as an illustration. In 2007, on this tree, there was a lot of slime over the moss. When we came back in 2017, there was still a bit of slime, but we could see signs of recovery from mosses going in. What we now hope is that in the future, when the air concentrations stay low, that we go to a healthy tree lichen community. If that will be the case, we have to wait for it. Next slide, please. And I'm handing over to Uli.
So we've been doing the ammonia monitoring in local mini networks around a lot of these designated sites you can see on the map for a while now. So there are 10 sites of European importance. There is Ballynahoon Bog, which was the first one in the center here. which we've been monitoring since 2014, so it's coming up to 10 years next year. And at the various sites under the CAN project, Curran Bog, which is just south of Ballinahone, Gary Bog up in the north, Moneygall in the west, Peatlands Park just south of Lough Neagh, and the upland side of Slieve Bay further south, as well as to Menon to the east, and also further collaborations with Ulster Wildlife and the National Trust at Coolka Mountain, which Nettie has just explained, and more newly established at Murlough and Slieve Donard in the southeast. So overall, we've got 4 to 9 samplers per site in these places. And we are doing monthly monitoring with samplers that are really simple and easy and don't need any electricity. And also just to point out, so all the orange sites or amber sites have just got ammonia monitors. The blue site, Coolka Mountain, also has the wet deposition, and Ballinahone has both of those and also NO2 sampling to see what is coming in from the combustion sources. Next slide, please. So some examples of average annual ammonia concentrations from some of these sites, and you can see blue on the right-hand side in Slieve Bay, that's quite clean. And then yellow, amber, red and purple, that shows how where it is potentially really quite dirty. And you can see Curran Bog, there is one source, and we've got a really nice, from a scientific perspective, gradient from site 1 where it's purple, and it gets then cleaner as you go further away with the prevailing wind. Peatlands Park is quite complicated. The annual concentrations don't show quite how complicated it is, but there's lots of potential local sources all around the bog. Whereas Ballinahone, again, you can see there's a gradient of sites from 1 to 5, where there is a farm just upwind, and there's another farm a bit further to the west, and site 8 was set up as what we call a background site, which is relatively clean and away from any local hotspot sources. And as you can see, the average annual concentrations that are shown here, they're obviously averages, so they tend to underestimate seasonal peaks, and I'll show more of that in the next slides. Next slide, please. So here's an example of Curran Bog. You can see the little gradient of sites from the south west to the northeast, and the blue dots are where there are livestock houses. And site 5 is a bit further away. You can see on the right-hand side the map of modelled concentrations. This is an older map than the ones I showed you earlier. But you can see that on average we're expecting from the modelling the annual concentrations to be between 2 and 3 to the north and 3 to 4 micrograms a bit further south. And if you click again, please, Claire. So these are the average concentrations at the 5 sites. You can see CB1, the one with the high concentrations. So these are the average concentrations in the box there. But then you can see what's called the whiskers, so the stalks coming out and the roots going down. That's the minimum and maximum of the 12 months that make up the annual average concentrations. So you can see that in the high concentration months, it goes really high, above 20 micrograms. And in the low concentration months, site 1 is down to, I guess, 2.5 micrograms, whereas the other 4 sites further away from the sources are much less influenced by that source and have a much narrower range. And you can also see just how quickly that gradient drops from close to the source to a bit further away. But there is a tail to it as well, so it doesn't get clean by site 4. Next slide, please. This just briefly shows what I was saying about the monthly variability, the seasonal variability. So again, site 1, the one closest to the source, the pink line, you can see a really high peak in March. So there must have been slurry spreading very close to that site on the boundary of the SAC. And you can also see probably where the livestock house was full, you can see concentrations from that over the winter. And the other sites are much lower, but you can see the slurry spreading peak comes across at most of the sites except for CB5, which must have been a little bit more sheltered. Next slide, please. Another site, Turmennen, has got quite a different system here. So if you can see in the photo, to the southwest of the site, there's a lot of shrubbery, so it doesn't have sources nearby. The main source nearby is to the east, those really quite green fields, which get a lot of slurry. And you can really see that nicely in the monthly graph, that March had a quite high concentrations there. But it would also be relatively easily fixed by, for example, using low emission slurry spreading in those fields. And you can also see the gradients with sites 1, 2, and 3. So the ones furthest away from the field and close to that shrubbery that protects them a little bit, those are much cleaner and actually below the 1 microgram critical level for at least part of the year. Next slide, please. So it's great to have data for a year, but it's even greater to have data for multiple years and to see just how things vary between years. So Ballynahoon Bog, you can see that cluster of measurements that's happening there at all sites. And the graph has summarized data from all the measurement sites for each month. So you can see, for example, 2019, there was a really high March peak with slurry spreading. And the other years are kind of showing similar patterns, except in 2018, the pink line, there was some pollution event going on in the autumn. That was very odd, and we never quite got to the bottom what happened here. But you can see there are general patterns and then there are exceptions. Next slide, please. I suppose we should move on a bit faster as well because time is running. What we also have at Ballynahoon is a MET station where we can look at the wind patterns. You can see the little wind roses next to the different months and just how different they are. So for example, in February, there were a lot of easterly and southeasterly winds, whereas in March, it was more southwesterlies. And then we can look at the concentration gradients across the sites and try to explain what's happening here. So the wind data is really helpful for that. Next slide, please. Something else we've done on Ballynahoon, where we've got not just the ammonia measurements, but also the NO2, so the combustion concentrations, and wet deposition measurements. We've tried to do a budget by calculating what comes in through atmospheric deposition. You can convert concentrations to deposition by using something called deposition velocity estimates. And the main message here is that the measured deposition on the top left-hand side, that pie chart, if you look at the proportions of the different types of nitrogen, the by far biggest one is the dry deposition of ammonia, which comes mainly from those local sources, with the other 3 parts, the 2 types of wet deposition and the dry NOx deposition being relatively much smaller. And if you then look at the top right-hand one, that is for another part of the bog. So the wet deposition and the NOx dry deposition, they are varying much less spatially than the dry ammonia deposition. And because we've got so many sites where we measure ammonia concentrations, we can then calculate different dry depositions for each of those sites. So the ones closest to the source and the ones further away. But as you can see, the overall pattern is still the same. It's just there is even more in total kilograms. So you get the 21 kilograms at the maximum dry deposition site and the 10 kilograms at the minimum dry deposition site. And then we've also estimated from the modeling, which is area weighted and which is has much less detailed input data. And the really reassuring thing there is, if you look at the bottom of the table, that the measured and the modeled are within the same ballpark. They're within the same range, and obviously the modeled has a much narrower range, because when you're just modeling the bigger picture, it doesn't vary so much. Whereas if we take into account the local spatial variability for the dry deposition, then you can see that the real pattern is just more varied for the dry deposition of ammonia. So that really points to the importance of knowing about your local sources. Next slide, please. And just to say, it was very reassuring to see just how well the model and measured data match together. So zooming back out again, where does Northern Ireland's N deposition come from? It's obviously not just the local sources. And we have some estimates based on 2018 data. So if we just focus on the maps first, you can see this is total nitrogen deposition. And you can see the sort of red circular arrow on the left. This is the Northern Ireland gives itself 6.3 kilotons of nitrogen deposition every year. It also exports quite a sort of large arrow over to Scotland, because that's just downwind across the Irish Sea, and some smaller bits get exported into England and Wales. In terms of what gets imported into Northern Ireland from elsewhere, there is a good proportion that comes in from the Republic of Ireland, but that is much smaller than what Northern Ireland gives itself. And then there is some import from Scotland, but much smaller because it's downwind rather than upwind. So overall, Northern Ireland exports way more nitrogen to the rest of the UK than it receives from the UK and from elsewhere, which includes the Republic of Ireland. 92% of the nitrogen originating and redeposited in Northern Ireland is from ammonia, with only 8% from the NOx. So it's really the agriculture rather than the combustion that is depositing in Northern Ireland. And also one further sort of key statistic, that of the ammonia-related deposition that's landing in Northern Ireland, well over 2/3 comes from sources within Northern Ireland, and only that last, well, it's actually more, a quarter, is coming from outside Northern Ireland. And I think that's where I hand over again. Next slide, please.
Okay, thank you very much to Anya, Uli and Nettie for covering a lot of the detail that we immerse ourselves in regularly. And so I do know that that's an awful lot for folk to have taken in. And again, we can share slides and share more detail on this one. But I suppose we just want to acknowledge here, first of all, I suppose Anya's key role as our lead scientist on this within NIA, the key role and collaborative partnership that we have with CEH, and also the assistance that we've been getting from Ulster Wildlife National Trust, Monaghan County Council, and also from Mananoma to assist with the collection of the data. And as you can see, it's quite an interesting picture when you do start to look at that level of detail. Even just nationally at a scale, you can see how challenging it is going to be for us to address this issue. We've been talking about ammonia for a very long time, and there the latest report shows that I suppose we still have, it's increased again, and we're still at the highest level. So again, it's something that we need to get on top of. But when we also look at the level of data and the interesting, I suppose, figures around wet and dry deposition at site level, that really does start to give you a picture around the types of measures and very targeted measures that actually could reap dividends much more quickly. So it's around how do we start to use that in a way that allows us to protect those areas that we're going to need to restore, both for biodiversity but also for climate change mitigation and adaptation. It does highlight that key role of the importance of addressing pollution, and most notably nutrient pollution, for us to be able to meet and deliver any of our statutory obligations that we have already for protecting our site network, and getting them restored, but also how do we meet those obligations under the Climate Change Act, where we're just not able to suppose see the outcomes where we do get that investment and restoration. So I think it's invaluable data going forward, and I think it will be key to make sure that we maintain that. Again, a lot of very valuable data that I think a lot within the department will be interested in seeing, and will want to kind of dig further down into to see how do we use that to inform current investment programs, and a lot of our conservation works as well. I suppose I really wanted to kind of open this up for questions. I appreciate that today's presentation was pretty technical, and folk may not want to have got into any detail or start to explore some of the specialist nature of some of that data around wet and dry deposition and the impacts on various species. But if others do want to ask some general questions around how do we start to target these measures and how do we use it to inform policy, please feel free to put a chat in the question, a question actually in the Q&A section there. But I suppose, Uli, building on the work that you've been engaged with the rest of the UK, including taking forward the UK Nitrogen Futures project, where I suppose we've been playing our part because we've invested significantly at the department in gathering this type of data, which is incredibly valuable. How do you see that Nitrogen Futures work going forward and developing, and how are you seeing others? Sorry, I'm giving you a double-barreled question here. It's very rude of me, but how do you see other parts of the UK using this type of data to inform those kind of targeted measures and their various site nitrogen action plans?
Yeah, I'll try and remember both questions. So the first one was about Nitrogen Futures and what is that doing and taking forward. Probably a lot of people on the line don't know what Nitrogen Futures is. It's a project that does scenario modeling for 2030 and beyond to look at different futures depending on the types of mitigation and ambition of mitigation being taken forward. And we then calculate emission maps for those scenarios, concentration and deposition, and then we look at how much does that achieve in terms of reduction of concentration and deposition towards the critical loads and critical levels metrics. And then we also zoom into designated sites and see what would that do locally. So the message from the first Nitrogen Futures project, which is now a few years old, was that you really need a dual approach of ambitious measures everywhere, but then really focus the most ambitious measures as close as possible to your designated sites to really make that local difference for a hotspot where a source may be right next to a designated site boundary. And if you can bring that down, for example, thinking about Ballinahone or Curran Bog or somewhere, then you can really help that local endangered part of a bog or whatever type of habitat it is. So we are taking it forward now with a new modelling project, which takes account of new policy targets and checks what might those do. And also that includes thinking about what does the net zero do to air pollution. So obviously net zero is for climate change, and it's about, for example, electrifying the vehicle fleet or planting more trees, and how it matters where you put those measures. So for example, if you electrify the vehicle fleet, obviously that brings down the combustion emissions, which is great. If you plant more trees and you plant them to replace areas with high emissions, then again, that brings down the emissions. If you intensify some areas because you are needing to free up land for planting your trees or for doing something else, then that may potentially endanger sensitive habitats that are in those previously not intensified areas. So there's a lot of questions of what if in nitrogen futures, and yeah, that message of general need for reducing emissions everywhere, but also spatially targeting near the places that need it most. Other parts of the UK, for example, England and also now Wales increasingly are introducing and have gone quite far along in terms of England, in terms of introducing what's called shared nitrogen action plans, which are looking at a designated sites, a selection of them, and working with local stakeholders to identify what's happening there, what are the main sources, and what can be done to help mitigate the worst nitrogen pollution impacts.
Yes, and I think that's where we're going to need to ensure that any of our restoration projects, which will all be, expensive in many cases, that we'll need to find some way of having an accompanying set of measures to be able to address the local ammonia emissions for it to be able to deliver those objectives, because we are seeing even existing restoration activities currently being undermined, where we're still seeing worrying losses of sphagnum. So we do need that combined approach. Thank you, Uli. I see there have been a couple of questions in there. If I just see them popping up again. Yes, there's one from Rory. Have you a good understanding of the half-life of atmospheric nitrogen concentrations, so that if we were to stop emitting tomorrow, how long would it take us to get below critical levels and loads?
Okay, I can take that on the concentration side. So if it's like if you turn off a tap, so the ammonia concentrations in the air would go down instantly. It's then the key question is, how long would it take to then reduce the impact on the vegetation because of the nitrogen that's already in the system? And I guess the other thing, the caveat I should say is, if you turn off one source, there is still the background from the other sources nearby as well. So it doesn't just drop to zero, but that if you take a particular source out, it's like you have a chimney and you turn off your fire, then the smoke stops. It's that simple, really. But the vegetation question is much more difficult.
It is, and I think as we're finding from Nettie's work as well, that some of our sites are quite saturated with nitrogen, so we will need, as is always the case, the more evidence and research required, just to try and see what does that I suppose, saturation and high levels, embedded within these peatland systems, for example, how that will affect their restoration potential, which is one of the things that we're trying to address in a NERC funded mothership project. So we're trying to see what does that mean for the fate of our peatlands and how we're restoring them. There's another question here from Kevin around the evidence presented here and the department's call for evidence. I think I suppose the point here is that we do have, and I think it's well known that we have a lot of evidence around the impacts on our sites and also on the levels that we are picking up from these monitoring programs. I think the department's position is around to see is there any other evidence out there that can inform how we assess the potential impact from projects that and other plants that will be emitting ammonia. But again, I think it is recognised that we already have quite a lot, but it allows others to provide more evidence to us. But I think there's plenty already. There's already there plenty to go on, but we'll see what emerges from many others who are collecting data on the state of the natural environment and possibly on emissions. So you can never have too much evidence. Folks, I know we've just thank you very much for those questions. I want to take the opportunity to thank Anya, Oli and Nettie for their time for setting this all out. We will share the slides and also the link to the recording for anybody who needs it. But thank you very much for giving us your time to set this all out over your lunchtime, and look forward to continuing this conversation. Thank you, everyone. Good afternoon.
Thank you. Thanks, everyone.